Hello everyone, in this video we're going to be looking at section 11.1 and continue where we left off with vector operations. Okay, so definitions of vector addition and scalar multiplication. Let u and v be vectors with those components and c be a scalar. The vector sum of u and v is the vector u plus v, and all we do is just add the first components and add the second components, right? Fairly simple. Okay, so now let's talk about what this looks like visually. So the sum of two vectors can be represented geometrically by positioning, by positioning the vectors without changing their magnitudes or directions so that the initial point of one coincides with the terminal point of the other. Okay, so before we do that, let's go ahead and just draw, here's our coordinate plane. Let's draw vector u. Let's say u is maybe this vector, and then let's say v is maybe this vector, right? So what we're going to do to add these two vectors is we put the initial point of one at the terminal point of another. So for example here, let's say, let's do this. Let's take our u vector, which is this guy, and what we're going to do is now tip to tail is how I always kind of think about this. I'm going to tip to tail put that vector there, and now I think I'm going to have to scoot everything over to fit all I want in here. And now what the sum vector is, you take the initial point of u and the terminal point of v, so it ends up looking like this vector right here. So this is the vector u plus v. I can write it like that, or I can write it as u plus v all underneath the vector, so I personally like the first way, right? So that's the idea behind adding and subtracting vectors. And then one thing to notice too, so again, this right here, looking at the other bullet point, the vector u plus v is called the resultant vector. So this is the resultant vector, right? And it is actually the diagonal of a parallelogram, right? So let's take that there. Let's get rid of all this info here. And then let's get all of our vectors again. Let's get v again. But this time I'm going to put v down here. And this time I'm going to put u up here. And notice now I have, let's get rid of u, sorry. And now I have a parallelogram. Right? So this is v, and this is u. And so the point of this is to say that resultant vector, or that sum vector, is just going to be the diagonal of a parallelogram having u and v as its adjacent sides. Right? So this guy right here is a parallelogram. Cool. Okay, so the scalar multiple of c and u is the vector c times u, which is just taking the first component multiplied times c and then the second component multiplied by c. Geometrically, what this looks like is just means that I have the absolute value of c times as long as u. So for example, if I had the vector 2u, then the vector 2u would look like this. The vector 2u would be, whoops, did the wrong thing. Vector 2, well, actually let's do 2v because it's flatter. It'll be easier to put on the paper. Wow. Why is that not doing what I want? Don't know what's going on here. Try this again. So copy, paste, and then paste. This would be 2u. This whole vector here would be 2u. I'm sorry, not 2u, 2v, because it's twice as long as v, right? So that we'll put up here. Okay, so that's the idea. If C is positive, then CU goes in the same direction. If C is negative, then CU goes in the opposite direction, right? The negative of a vector is negative v, which is just negative 1 times v. In other words, just take the components and put a negative sign in front of them. So for example, the negative of u would look something like, it would be in the same, it had the same magnitude, but it would be in the opposite direction. So this would be like negative u, right? And then the difference of u and v is the vector u minus v, which is u plus negative v. We know what negative v is. We know what u plus v is. So essentially, you just subtract the first components and subtract the second components. So now let's talk about what this looks like. Sorry, I'm having so much trouble with this guy here. So this would be negative u. So let's look at this geometrically. So geometrically, say I had u and v just like I had before, right? So say I had, this is my coordinate plane here, and then I have u and v like I had before. So this is u, but I'm going to start it at the origin, and this is v, and I'm also going to start it at the origin. And then the idea here is if I had the difference of u and v is u plus negative v, right? So what is negative v? Well, remember, negative v is going to be the exact same magnitude and direction of v. So I'm going to try to draw this right below, sorry, the exact same magnitude, but the opposite direction, right? So that guy I drew in blue here is going to be negative v because it's the exact same length and direction because I drew it parallel, but it's the opposite, right? So this one is going to look like, picked up some other stuff. This one is going to look like, this is going to be negative v, right? Because if I want to add u plus negative v, remember I go tip to tail, right? So tip to tail, that's u plus negative v. And remember, what is their sum? Their sum is now going tip to tail. This is u plus negative v, right? And now notice I have like a parallelogram, and this guy right here is going to be the u minus v, right? Because this is the same as u minus v, right? So the idea behind the difference, I basically, what I do, instead of tip to tail, or I can think about it as tip to tail, like the addition with the negative of the one that's being subtracted, and then that ends up being basically the same, or it ends up being exactly the same as putting both at the origin and then doing the magnitude is the difference is the guy that goes in between these two, the guy that connects these two, which is this guy that I drew in purple dotted. Okay, so that is all of our the pictures of addition and scalar multiplication. Obviously, the pictures are kind of harder than all of the vector addition and scalar multiplication because basically vector and scalar addition, subtraction, and scalar multiplication, you just do component-wise, right? So it's really not too bad. All right, so let's look at this one. It's 1/2. It says for v equals to negative 2, 5, and w equals 3, 4. Find each of the vectors. Okay, so 1/2 v is going to be 1/2. What is v? V is the vector negative 2, 5. And what do? We just take the scalar and we put it in, multiply it in both components. So essentially it's like distributing it, right? So here I get 1/2 times -2, and then 1/2 times 5. So I end up getting that this is -1 and 5/2. So that is the vector 1/2 times v. Okay, so now let's look at w minus v. So w minus v looks like w is 3/4 minus -2, 5. So then what I do, I just subtract their first components and second components. So I get 3 minus -2 and 4 minus 5. So I end up getting 5 and -1 here. Okay, and then finally, let's do v plus 2w. This one we're going to do maybe a little bit faster. So v is going to be -2, 5 plus 2 times w, which is 3, 4. So now instead of writing out distributing, let's just do it. So this one ends up being -2, 5, and then if I distributed my 2, I would get 6 and 8. And then now, finally, let's just add component-wise, right? If I'm adding two things, I just add component-wise. So again, let's not write out the steps. Let's just do it. So -2 plus 6 is going to be +4. And 5 plus 8 is going to give me +13. Right? So 4 +13 is going to be that vector, v plus 2w. Okay, properties of vector operations. Let u, v, and w be vectors and c and d be scalars. What do we have? We have addition is commutative, right? This is a commutative property. The second one is an associative property. The third one is that we have an additive unit. So in other words, we can add, if we add the 0 vector to u, we get u back. The fourth one is that I have an additive inverse. So I can always find somebody that's going to give me 0. And then C or 5 is basically saying that I can have associative property with my scalars. 6 is saying that I have the distributive property for my scalars. 7 is another type of distributive property for the scalars. And then 8 is just saying that 1 times u is u, so that's like a multiplicative identity. And then 0 times u is the scalar. I'm sorry, this isn't a multiplicative identity. This says that the scalar 1 leaves everybody alone, and the scalar 0 takes everybody to 0. So those are some properties. The length of a scalar multiple. So remember, what do I do in order to find the length of a scalar multiple? If I want to find the length of c times v, well, it's just the absolute value of c times the magnitude of v. And sometimes that's easier than finding the magnitude of CV. And another really important one here is 11.3. Theorem 11.3, it's the unit vector in the direction of v. So if v is a non-zero vector in the plane, then the vector that is defined as u equals v over the magnitude of v. Remember, the magnitude of v is a scalar. Right? So what I do in this second one, this is typically the one I use, is that u is equal to 1 over v times 1 over the magnitude of v times v. That's just going to be, this whole thing is a scalar. And then we multiply a scalar times a vector, so that gives us another vector. Right? So this vector v that is defined as 1 over the magnitude of v times v has length 1, and it is in the same direction as v, right? Why is that convenient? Well, sometimes putting it at, or making it the same direction is really nice, because then they are kind of like equivalent, and these aren't equivalent because they don't have the same length, but they have the length. So if I'm talking about u and v are not equivalent because they don't have the same length, but they're almost equivalent because they have the same direction. But it's convenient that they have length 1, because length 1 is any vector that has length 1 is called a unit vector, right? So u, this guy that is this guy u that's defined as 1 over the magnitude of v times v is called the unit vector in the direction of v, because it's in the direction of v because I'm multiplying it times v, and this 1 over the absolute value of v means that the magnitude, that kind of scales down the magnitude so that it has a magnitude of 1. So again, the process of multiplying by 1 over the magnitude of v is called the normalization of the vector v, but again, it just means shrinking it down to being of length 1. Right? So example, if this was my big old v, then u is just the unit vector is this guy, so it's the same direction, except the magnitude of u is going to be 1. So it's just like shrinking down a vector. Okay, so now the question is to find a unit vector in the direction of v and verify that it has length 1. Right? So again, to find the unit vector, so v is that, to find the unit vector in the direction of v is going to be 1 over the magnitude of v times the vector v, which in this case, I don't know why that's not doing that. In this case is going to be -2 and 5. Right? So first I got to find the magnitude of v. So the magnitude of v, how do we do that? Remember, it's just the first component squared plus the second component squared underneath the square root. So this is 2 squared plus, or I'm sorry, -2 squared plus 5 squared underneath the square root. So I get 4 plus 25 underneath the square root, so I get the radical 29. Right? So if I was going to find u, it's 1 over radical 29. Again, that's just a scalar. It's a really awkward scalar, but it's a scalar. And then I'm multiplying it times the vector v, which is -2, 5. And remember, what do we do with scalars? We distribute it inside. So this ends up being the vector -2 over radical 29 and 5 over radical 29. Oftentimes, these unit vectors in the same direction tend to be kind of ugly like that because you always are going to have a radical when you do the magnitude, unless it's a perfect square. All right, so that is the unit vector in the direction of v, which is to -5. Okay, and then we want to verify that it has length 1. So we want to verify that the magnitude of u, which is that guy that we just found, is equal to 1. So that magnitude, remember, is the first component squared plus the second component squared underneath the square root. So the first component is -2 over radical 29 squared plus 5 over radical 29 squared, all underneath the square root. So that is going to give me positive 4 over 29, right? When I square 2, I get 2. Or when I square 2, I get 4. When I square radical 29, I get 29. Plus 25 over 29. And if I add those up, notice they have the same common denominator. So it's the square root of 29 over 29, which is the square root of 1, which is just 1. So indeed, this vector u that we found does have a length of 1, like we expected it to. Okay, so generally the length of the sum of two vectors is not equal to the sum of their lengths. To see this, let's consider the vectors u and v as shown below. So let's do this. Let's say I have u, which is this guy, and v, which is this guy. And so the basically what I'm trying to explain here is that the sum of the two vectors is not equal to the sum of their lengths. So the sum vector, so if I think about this as a triangle, with u and v as two sides of the triangle, then this is my third side of the triangle, right? And this is that vector u plus v, right? The sum vector. But the length of this guy, remember the length is the magnitude. So the magnitude of u plus v is going to be less than or equal to this magnitude, which is u. The length of that guy is u, and the length of this guy, let's put v on here? Is it not working? Okay. We'll squeeze it in here. This is the magnitude of V, right? So the claim here is that in order for me, the distance traveled going over the blue, right? The distance traveled going over the blue is the magnitude of U plus V, so that's this guy, is less than or equal to the distance traveled if I traveled up orange and over green, right? If I walked up U and over V, that would be longer distance to walk than just walking the blue, right? The quickest way from point A to point B is walking a straight line, right? And so that is what's known as the triangle inequality, right? Is that if I go the two sides of a triangle, it's always going to be shorter, or I'm sorry, it's always going to be longer than just going the hypotenuse, right? This is the hypotenuse, this is going the orange distance, and this is going the green distance, right? So that's what's known as the triangle inequality for vectors. Okay, we'll go ahead and end this video here, and we'll pick up where we left off in the next video.